300, 538. Um, so in the event that you don't have the Top Hat app or don't go through Canvas, then and you're on like I don't know, an incognito browser or something like that. This is our join code, but I'm hoping that this will make things a little bit more smooth when it comes to transitions, and I won't have to toggle back and forth because there's always a lag time with that. I want to make this as seamless as possible. So with that in mind, we're going to go ahead and continue on what we were talking about last time. Last time we were talking about amino acids, and we talked about polar amino acids, our polar positive amino acids, our polar negative, and our polar uncharged amino acids. Now, today, we're going to add on to this, and what we're going to do is we're going to dig a little bit deeper. We're going to be talking about an isoelectric point. Now, by definition, an isoelectric point is the pH at which a molecule has a net charge of zero. Now, a very important detail there is net. So this is our absolute charge. So the overall or the summed charge is going to be zero. Now, does that mean that the molecule has no charges? No, it does not. This is, well, basically where it has no cumulative charge. Now, this is a property that's not unique to amino acids and not unique to biological molecules, but it's very important when it comes to biological. That's not working as well as I want it. Okay, let me change this one. Biological separations. Now, typically, when we're talking about an isoelectric point and interested in an isoelectric point, we're also a little bit more interested in proteins. Now, and I think that a very good example and visual of this is, has anyone ever added vinegar to milk or acidified milk, sorry. Has anyone ever done that? And if so, or can you imagine what happens? It curdles. Andrew, that's absolutely right. And the reason that it curdles is because, does anyone know our major proteins in milk? Casein is one, absolutely. And whenever you add vinegar or acetic acid or heck, any acid to milk, the curdling is casein precipitating. Okay. Now, the reason that it's precipitating is because you're getting close to the isoelectric point of casein. Now, what do you think that means with respect to if a molecule is at its if a molecule reaches its isoelectric point, what do you think that means in terms of its solubility? Is it soluble or insoluble? And of course, there's a spectrum there, but if we were to put it in one party or one camp, well, it'd be casein's going to be insoluble because it precipitates, it clumps out. It would be insoluble as you approach the isoelectric point. So essentially what that means is if you're ever trying to separate a protein from a complex mixture, if you can get that protein to reach its isoelectric point, well, then that protein's going to precipitate out a solution. And so that makes it super easy for you to remove that thing. Because if you think back to like Gen Chem 2, I know, and any other lab period for that matter, one of the important things that you learn about is separations. So you're taking this substance, you have your supernatant and your pellet. And effectively, whenever you acidify milk, you make that casein part of the pellet, and then your whey proteins remain soluble. So understanding an isoelectric point is super important for the purposes of separations. Because when it comes to studying biological molecules and studying proteins, what we want to do is be able to separate proteins from a complex mixture. Now, when it comes to calculating and looking at an isoelectric point, there are a bunch of amino acids that it's very easy to understand their ionization and understand how to calculate their isoelectric point. Now we group those as our diprotic amino acids. I have up here the single letter codes for all of our diprotic amino acids. The only pKa values, because your pKa value is what's very important for calculating an isoelectric point, because an isoelectric point is the pH measurement, or is a pH measurement. All of these have only two pKa values. But then we've also got our triprotic amino acids. Now, last time what we kind of narrowed in on was we talked about our positive amino acids, arginine, lysine, and histidine. And we also talked about our negative amino acids, aspartic acid and glutamic acid. Now I bring up two other amino acids, tyrosine and cysteine, because these two amino acids are ionizable, but their pKa values are higher, so they are going to remain protonated, albeit uncharged, at a up until a higher pH. Now, with that said, these are our seven ionizable or our seven triprotic amino acids. So when it comes to calculating a pi, you have three pKa values, an N terminal, a C terminal, and an R group pKa value. But for calculating a pi, you do not need all of them. You only need two pKa values. And I haven't shown you the calculation, but we're going to get to that. So essentially what this means is you've got your diprotic amino acids where you only need two pKa values, and then your triprotic amino acids where you, again, only need two, but you have to be kind of critical of which ones you actually need. Now, here is our first question, just a little bit of a review. So, which amino acid from the list that's shown below is a polar positive residue? Oh, strange. Okay. So I've got these all set, all the questions set to have 1 minute on them. And should I need, I can add 15 seconds or so. But I think 1 minute's adequate to answer this sort of question.
Yeah, no, it'll be all right. And we don't have teams right now, so it's like. 'I know, because I was like, oh, I'm at 40, I got
10 seconds left. Let's see, are we going to get all 63 participants? I think we are. Four, three, three left, two. Close, close. We got, stop. Okay, we got 62 participants. That's pretty good. All right, so our single letter code for our positive amino acid here is lysine. I think the question's closed, correct? There we go. Okay, so when it comes to identifying the positive amino acids, we're really looking at that R group. Lysine is the only one of these amino acids that has a positively charged or a potentially positively charged R group. Cysteine at a physiological pH is going to be neutral. Aspartic acid, D, is a negative amino acid, and alanine is an amino acid that's a polar or a non-polar amino acid. That's A. Okay, so now proceed to next or our next kind of progression. So when we look at And this is one thing I did notice yesterday whenever I was integrating all of my PowerPoint slides into Top Hat. I'm sorry, but this font right here, I guess it's one that's not a part of Top Hat's font package, so it's a little bit distorted, and I apologize for that. So some of the letters don't appear as you would expect. But if you're looking at the PDF, those are vector images, so you shouldn't have any loss of resolution there. Now, here are diprotic amino acids. And one of the things that's really important for you to know is to be able to kind of predict or anticipate pKa values. I'm never going to ask a question, what is the pKa value of this? Where I'm looking for, well, 2.33 versus 2.32. I'm never going to ask that question. I will, however, ask a question, you know, I'll give you a couple of different answer options. B, C, I'll give you these options. pKa of a C termini. So the carboxylic acid that's on the right-hand side of your amino acid, if I were to give you options like 2.30, 6, that's supposed to be a 6.14, and 9.5. This is a question where really what I'm getting at is, can you discern the differences between these? Can you kind of anticipate and think about, well, what does that functional group look like? What is that functional group's pKa value typically? And go from there. And this is one that when you're looking at the pKa values of your C termini of your amino acids, if you look at all of these, they range from, let's see, our lowest is, I think it's 2.00, and our highest is 2.58. So I want you to know that it's within a very narrow range. It would not be 6 or anything like that. Then your N termini, the group, your amino group on the left-hand side of your molecule, well, these range from about 8.8 to 10.6. These have a little bit more of a broad range, but I still want you to have like a sense of where that is. So my question for that would be something like your pKa value for an amino group on an amino acid would be 1, 3, 9, 14. And then I would want you to process that information and think, well, it's not going to be 1 because that's way too low. It's not going to be 3 because that would be acidic. 14 would be excessively basic. I'm going to go about 9.5. And typically, if you're preparing for any sort of standardized exam or something like that, or if you were to take any other biochemistry class, whether that's in graduate school, which, yeah, I had to take biochemistry classes as a biochemistry graduate student, or medical school, you're going to look at the N termini as approximately 9 and the C termini as approximately 2. So those are kind of the rounded numbers. Now, my point of showing you this is one, I will always give you those pKa values. Any questions where the pKa values are necessary, I'm going to provide those to you. And these are the numbers that I'm going to provide you with. If you pull up a biochemistry textbook or look for any other resources online, you're going to find numbers that might vary a little bit. But at the end of the day, this is a molecule, or all of these molecules, all these diprotic amino acids, they're going to have titration curves that look a little bit like this. I'm marking off my 2 pKa values, and then I'm going to draw in my buffering range, then where it rapidly increases, my second buffering range, and there we go. So over here, where I'm going to put and do my dashed lines, then I'm going to do my other dashed lines, where I'm going to label A. That's my fully deprotonated form of all of these amino acids. B, from dashed line to dashed line, is where my C termini, my predominant form, is deprotonated at the C termini, and then this part C from dashed line on into infinity, well, then my molecule is going to be deprotonated, so fully protonated, full deprot. So this is what your titration curve for a diprotic amino acid is going to look like, or heck, any diprotic acid. That's what this is going to look like. Now, our fully protonated forms of all of these diprotic amino acids, it's going to have a charge of +1. And being able to understand these charges is really important. The predominant form in this B range is going to have an overall charge of, or predominant form is going to have a charge that is 0. And that's because you have your N termini and your C termini right here that are fully, right here, where the N termini is protonated and the C termini is protonated. So just as a kind of general backbone, what that's going to look like is this. My C termini is protonated. H3 plus, and then I'm just going to draw an R group. So as you can see, this carboxylic acid is protonated, but it's neutral. My N termini is protonated and it has a positive charge. So the predominant form within range A is going to look exactly like this. Now the predominant form in range B is going to look like this. So I'll continue by dashed lines up here. H3N plus C O minus and R. Okay, so now my carboxylic acid is deprotonated but my amino group is remains protonated. The predominant form within range B looks like this. Now, range C is where we've got the predominant form is fully deprotonated. And that's going to look like this, H2N C O minus, and there's my R group. Now, the key of all of this is that my R group is not a part of the calculation, not a part of the equation, because these R groups, whether they are polar, uncharged, or non-polar, they're not going to be deprotonated. In which case, my C range, my overall charge, or my predominant form, my overall charge is going to be -1. So effectively, what we have are, let's just go with alanine right off the top. We have two pKa values that are very important. We have this 2.35 and this 9.87. So at the when the pH is equal to 2.35, we've got 50% of the molecule that looks like this, and then 50% of the molecule that looks like this. Right around 9.87, we've got 50% that looks like this, and 50% that looks like this. Now, just as a in the chat, what percentage of my molecule looks like that in form A, or in that range A? If my pH is 9.87. If my pH is 9.87, I've got 50% that looks like B and 50% looks like C. So what, Morgan, perfect. You're absolutely right. 0% of my molecule effectively looks like molecule A. So great job. Okay, now this is basically a diprotic amino acid or a diprotic acid. And when we talk about pKs, it's kind of simple and straightforward to talk about, okay, well, here's where my molecule is. I've got 50% that looks like this and 50% that looks like this. If I were to put an X right here, then, you know, that would be like 60% looks like B, and then about 40% looks like A. Great. As I continue to the right, what's going to happen to my fraction that looks like molecule A? Is it going to go up or is it going to go down as I move to the right on my titration curve? It's going to go down, okay? Now, there is going to be a point where I'm not going to have, or I'm going to effectively have 100% of my molecule that looks like B. Now, that point is going to look, or it's going to be approximately right here. That's right. On my x-axis equals 1. That's where I have 100% of my molecule that looks like B. Now, can you calculate approximately what that value is?
Okay, and then like slide 13, I guess you want a new,
Given the information that's on the slide, 9.87 and 2.35. Would you agree that that point is right between those two values?
like we can take out.
Great.
Yeah.
So what we can do is we can take those two numbers, 9.87 and 2.35, add those up and divide by 2. Those are our two pKa values and average them. Absolutely, Morgan. So when we get an average of those two, what we can say is 6.11. So this is our PI. This is a point where we can say 100% of my molecule looks like molecule B. Effectively, 0% of it looks like A, and 0% of it looks like C. 100% of my molecule looks like B.
But I'll be right here.
What we are accounting for there, and what we can kind of, what I always like to do is I like to make a number line, and I like to map out my charges. My molecule has a charge range of point +1. Whenever it's deprotonated, 0, and then whenever it's fully deprotonated, it's -1. This is really helpful for me because it helps me illustrate, well, what are the possible charges for my molecule? My molecule, can it be +2? No, it can't. Can it be -2? No, it can't. These are the possible ranges and the parameters that my molecule can exist in. Now, the next thing that I like to do is I like to take this number line that I just put together and write my pKa values, 2.35 and 9.87. Well, midway between 2.35 and 9.87 is where I can arrive at my PI, my isoelectric point. 2.35, 9.87, add those up, divide those by 2. Now, the significance of this is really more in the charges and a little bit less in the number of pKa values. So I've found what pH related to my pKa, my molecule goes from a +1 to 0, and my other pKa, where my molecule goes from 0 to -1. And those are 2.35 and 9.87 respectively. So the equation for a PI looks like this. pKa 1 plus pKa 2 divided by 2. That's where 100% of my molecule is fully deprotonated. Now I'm about to clear all those drawings or these writings up from this slide. Does anyone have any questions about this? Okay, clear all my drawings. And now it gets a little bit trickier when it comes to a triprotic amino acid. Okay, so our triprotic amino acids, we'll do lysine in just a second. I'll give you the overall view of what a triprotic amino acid titration curve is going to look like. You have 3 pKa values. Boom, boom, boom. Now, if we reflect on our diprotic amino acids and compare those to our triprotic amino acids, the N termini, well, they're not too radically different. I mean, the range might be a little bit more broad, but that's about it. The C termini, the range is also a little bit more broad. But when it comes to when it comes to your amino acids, you can look at your N termini as being approximately 9 and your C termini as approximately 2. So That's one thing that's constant. Now, our third pKa values, our pKa values for our R groups. Let's look at these. Well, we've got the pKa for the R group for cysteine. That's 8, okay? The pKa for aspartic and glutamic acid, those are 3.86 and 4.07. So those are around 4. The pKa for histidine is about 6. Lysine is 10.5. Oh, and before we proceed from there, that 10.5, that's higher than my pKa for my N-termini. Arginine, my pKa for my R group is also higher than the pKa for my N-termini. And same thing for tyrosine. So what I want you to take away from this is that there are some pKas that are low. There's one pKa that's kind of mid-range. And then there are other pKs that are actually higher, not only higher relative to the other R groups, but higher relative to the N-termini. So what that means is our triprotic amino acids, they're a little bit complicated. So we're going to go through an example. We're going to look at lysine. But our triprotic amino acid titration curves are all going to kind of look like this. They've got, what I want you to take away from this is that they have 3 buffering ranges. Now, in terms of charge possibilities, let's look at lysine. So I'm going to jump ahead and look at lysine's titration curve. Now, again, I apologize for the markings here, the font not carrying over, the typeface. Get the terms typeface and font mixed up. So this is lysine. Got it up here. Now, lysine, the way that some people like to draw lysine is they like to draw it as their alpha carbon and then CH2, and then they put 4 and then NH3 plus. Okay. Now, what I'm going to do is I'm going to take lysine single letter code K, and I'm going to map out my pKa values. I've got 2.18, 8.95, and then 10.53. All right. Now, I'll just draw in this molecule, or no, I gotta erase that. That didn't look good. I'll draw in my curves. Great. Oh, buffering range, not as well as I wanted to draw there. But let's look at, I'm going to go ahead and draw my dashed lines on my, or according to my pKa values. And any scaling that's off here, I apologize for that. So I'm going to go ahead and draw A, or I'm going to write A, B, C, D. These are my different variations of my molecule. Now, molecule A is fully protonated. So arguably, what I've got here already is molecule A. So what's the charge on molecule A? The overall charge on molecule A? +2. Okay. So the first group, I always like to kind of rank them whenever I look at a molecule or it's fully protonated. I rank the groups that are and list them in sequence that they're going to be deprotonated. My C termini is my first group that's going to be deprotonated. And when that group gets deprotonated, my form B molecule is what I'm going to have, and that's going to have a charge of +1. Okay, now I'm also going to rank that on my list of pKa values. My next group that's going to be deprotonated, so my next highest pKa value is my N-termini. My third group is going to be my R group. Now, one of the things that I've heard people run into in the past as a pitfall is they say, oh, okay, so I'm going to deprotonate my C termini, then my N termini, then my R group. Well, if you look at the different pKa values, what you're looking at is them going up sequentially. Now, sometimes that is CNR, sometimes that's CRN. So you have to be kind of thoughtful and deliberate whenever you're looking at your different pKa values. So my form B molecule is going to have an overall charge of 0. My form D is going to have an overall charge of -1. So I've listed the molecules, I've listed the groups in the sequence that they're going to be deprotonated. My N or my C termini, followed by my N termini, followed by my R group. Now, I'm not so much stressed about drawing this molecule. What I'm much more interested in here is calculating my pi. Now, so keeping in mind what my pi is, it's the point where my molecule has an overall charge of 0. I've got, would anyone care to, based on these pKa values for lysine, add to the chat what that pKa value is, or that pi is approximately? Do the calculation. 7.22. Awesome. So essentially, one way that you could kind of look at that is, well, let's see our pKa values. So we've got 2.18, 8.95, and then 10.53. So if we take 10.53 plus 8.95, because what we're looking for is we're wanting a pH right around here, because that's where 100% of my molecule has a 0 charge. Now, I'm guessing when you got 7.22, you took 9.74. That's correct. So the 7.22, that was probably from 8.95 plus 2.18, or was that from all three pKa values? Okay. So the significance of the pi, and this is where it gets tricky. The significance of the pi has to do with the solubility of my molecule. And my molecule is least soluble. It precipitates out of the solution whenever it's reached its pi. And its pi is where it has no charge whatsoever, where 100% of my molecule has 0 charge. So what I want to do is I take this, in this case, I take my two highest pKa values. It doesn't matter where they're coming from. And that's another thing where people, they kind of fall into a trap. They think, oh, well, I got to use my N and my C termini. Nope. What you have to do is rank your charges. So this is why I always like to do a number line. I like to say +2, +1, 0, and -1. I'll switch my colors. And the next thing that I'm going to write in is I'm going to write my pKa values in increasing order. 2.18, 8.95, 10.53. So what I care about is I want my 100% of my molecule to have a 0 charge. So I'm going to take this pKa and this pKa, add them up, and I'm going to get 19.48. And then I divide that by 2, because that's going to get me the place right between those two numbers. And it's going to be approximately 9.74. So essentially, another way of wording that is my molecule is least soluble at a pH of 9.74. Morgan, absolutely. That's absolutely right. So if we wanted 100% of our molecule to be +1, like Morgan's asking, then we would say we would get our protein and adjust it to a pH of approximately, that would be, I believe that would be that 7.22. Now, I'm happy that you asked that, because one very common practice in biochemistry and any sort of separations is to separate based on charge. And so if you're trying to, use what's known as ion exchange chromatography to separate your protein from another protein, well, you can adjust and you can say, I know that at pH of 7.22, 100% of my molecule has a plus one charge. Is it the only molecule that has a positive charge or that has a charge of plus one? No, it is not. But I know 100% of my molecule that I'm trying to purify has that plus one charge. That's a fantastic question, Morgan. Thank you very much. That's a great question. Okay, does anyone have any questions about this? Okay, well then we will proceed. And I didn't clear my drawings, but nope. Okay, so here what I want to do is clear all my drawings. So here what we have is aspartic acid. Now aspartic acid, and yeah, we've got aspartic acid and tyrosine as other examples. Now I bring up aspartic acid because what I want to do is just walk through the charges and the charge sequence. This form of my molecule right here. This is where my molecule has a 100%, or sorry, this form of my molecule is fully protonated. What is, and this is a triprotic amino acid, what's the charge of this molecule as it's displayed right here? It's plus one. Absolutely. Okay. So then the first group to get deprotonated is this one right here. The second group to get deprotonated is my other carboxylic acid right there. And then my third group is my N-termini. Now, I'm not to avoid toggling back and forth between slides, I'll just give you some rough estimations. This is about 2. I'll just call it 2.1. This is about 3.9. And then this, I'll just simplify and say that it's about 9.1. Okay. Now, let's think about our charges. This is where my molecule, as it's displayed right here, has a charge of plus one. When my C-termini gets deprotonated, my molecule is going to have a charge of minus or of 0. Then, when I get deprotonated in the second position, it's going to have a charge of minus 1. And then my third position is going to have a charge of minus 2. Okay. Now, my pKa values that matter for this. Sure, I've got 3 of them, but the ones that really matter to me are going to be 2.1, 3.9, and that's it. Do I care about the 9.1? Do I care about deprotonating the N-termini form or N-termini of my molecule whenever I'm looking for my PI? I don't. So I'll write in 9.1, but I don't really care about that. So the PI for this molecule is going to be just about 3, which is halfway between my plus 1 and minus 1 form of my molecule. So this is the sort of calculation that I think is very helpful. And putting something like this together is going to save you a lot of time and energy because you can just say, okay, well, this exact same charge range is true of aspartic acid and glutamic acid. Now, if we go on to our next amino acid, we've got tyrosine. Okay. Would anyone add to the chat, if this is my fully protonated form, what are the possible charges for an amino acid like tyrosine? Or sorry, for the amino acid tyrosine. Plus one? Absolutely right. So could tyrosine ever be plus 2? Nope. Could it ever be minus 3? Nope. So then when it comes to calculating the PI of tyrosine, here's our first group, our second group, our third group. When we look at tyrosine, here's our first, our second lowest, and our third. Do we care that, or, when it comes to the calculation, do we care about the N termini versus the C termini? No, we don't. We just care about which numbers are basically the lowest because we know that we have a range of +1 to 0 to -1. And so we've got the 2.2 and 9.1. And I bring this up because where people run into problems is that they get this, they get these blinders on and they say, oh, well, I have to do the calculation with my C termini, then the N termini, then this. No, you don't. In addition to that, on Friday, I mentioned that I always like to show the amino acids the way that they're fully protonated. And the reason for that is to do calculations like this, to determine easily and quickly what is the pKa of that molecule. Or, I'm sorry, the pi of that molecule. Okay. So this is, okay, there we go. So there's how we calculate our isoelectric point. And, just as another example of that, this is effectively what we would do. Now, with that said, what is the isoelectric point of lysine? And so you can toggle back and forth. I'll add 15 seconds to this one just because of the possibility of toggling back and forth. Okay, so closed. 9.74. Great job. I just got a private message on an exam. Do we have to calculate or can we just memorize these isoelectric points? I would not spend the time memorizing it because I think that it's a little bit faster to, or it's a better use of your time to memorize the calculation and be able to critically think about those numbers than it is to memorize those. Um, and yeah, that's my opinion on that. So there you go. Okay, correct answer is 9.74. Good job. All right. Now we've got another question. And this one I'm not going to add the extra time because this one hopefully is pretty straightforward. All right. Let's check the responses. Okay. So the isoelectric point would not be either the pKa's. Instead, it's just those two pKa values added up divided by 2. The 2 and 10.6, those are just the values that are provided. It wouldn't be below because then you're talking about a molecule that has +1 charge. Okay, great. Now that we've talked about amino acids, the next progression is to talk about how an amino acid or how amino acids react with one another to form what's known as a peptide bond. Now, if you look at this, what we've got are two amino acids where the N termini and C termini of these molecules react with one another and in a condensation reaction to produce water and make a peptide bond. When we get into protein structure, we're going to get more into peptide bonds. But one thing that you need to know is that they are covalent bonds. These are strong bonds, and for properties that we'll talk about a little bit later on, they're particularly strong. So essentially what we have is a deprotonated carboxylic acid and a protonated amino group. They'll react, they'll produce water. It'll form something like this. Now, what we've got here is a protonated molecule, a protonated dipeptide. Now, calculating the pi or the charge for a molecule like this is basically the exact same as what we do for a single amino acid. Here, what we have is the dipeptide YE. So tyrosine followed by a glutamic acid. Proteins are read from what's known as the N termini to the C termini. So we start where there's a free amine and you look at, okay, what is the first amino acid? Then you find your peptide bond, which is right here. And then you say, what is the next amino acid? And that gives you your N to C terminal sequence. So here's the N termini, and here is your C termini. Now, one of the things that I want you to recognize, and that's good to recognize right here, is that we don't care about, or we no longer worry about the N and C termini of our individual amino acids because of the fact that they are both involved in a peptide bond. So when it comes to looking at the charge of this molecule, would anyone care to add to the chat what the overall charge of this molecule is as it's drawn? +1. You're absolutely right. Okay. So what we've got is our positive charge right here, our neutral R group, another neutral R group, and a neutral C termini. Now, when it comes to the N and C termini, the C termini of tyrosine, I don't care about that. My C termini of my peptide is the C termini of this. So I'm going to write 2.10. Then my R group for glutamic acid is 4.07. My R group for tyrosine is 10.07. And last but not least, my N termini of tyrosine is 9.11. So this molecule has a charge of +1 to 0. So I'm going to rank my groups in terms of how they're deprotonated. 1, 2, 3, 4. I scribbled out those groups that are involved in my peptide bond because they are no longer relevant to me. So I've got 4 groups. So if I want to draw my number line, this molecule can have a charge of +1 to -1 to -2 to -3. Okay. How many arrows did I draw there? And this is just kind of the little, I guess, trick that I use is I've drawn 4 arrows. I have 4 pKa values, 2.10, 4.07, 9.11, and 10.07. Can this peptide have a charge of +2? Nope. Can it have a charge of -4? Nope. Can I calculate my pi for this peptide? Yes, I can. By taking the exact same pKa values that I used for calculating the pi of an individual amino acid and adding them up and dividing by 2. So my pi for this molecule is approximately, let's see, 6.2, I'm going to call it. It's about 3.1. So that's what makes it a lot easier, or that's one thing that is very beneficial. Now, You know what? That's where I'm going to call it today. I'm going to stop my recording because it's 9:50 exactly. Um, I hope that you guys have a great day.